All right, so this is the last lecture in us talking about energy. We're still going to use these ideas moving forward when we talk about work and power, things like that. But just this introduction to the concept of energy and the conservation of energy, this will be pretty much the end of the basics. And hopefully this will be pretty short. Here I just want to talk about energy diagrams, what they are, how you can read them, that kind of thing. Okay, so okay. With energy diagrams, we're actually going to think about this in terms of potential energy. So the potential energy is the energy of position. You guys should remember that. Okay. So the idea of gravitational potential energy depends on the height of the object. So how much available energy is there if you were to release it. And then at the same time, we have elastic potential energy of a spring, which actually depends on its displacement from equilibrium. So in both cases, we have a height, we have a horizontal displacement from equilibrium. These are all positions. So an energy diagram actually shows a system's potential energy and total energy as a function of position. Okay, so we have the potential energy and total energy. Okay, so you might be asking, what about kinetic energy? And the reason we're not really considering kinetic energy here is that kinetic energy is the energy of motion. Remember, we have the whole 1/2 mv squared. Distance doesn't come into play for kinetic energy. That's why we're limiting this to potential energy. Okay, we actually have two energy diagrams over here on the right. We have one for a object in free fall. And we have another one for mass attached to a horizontal spring. So here's my spring and here's my mass. There's maybe the wall is attached to. So in both of these, we have some form of position, right? So here in the free fall example, on our x-axis, we're plotting height. And then down here, we're actually plotting the horizontal distance from displacement, so delta S. All right, so now the question is, well, okay, how are these plots useful? And we'll actually talk about both of these individually and go into more detail of exactly what we're looking at here. Okay. So in the energy diagram example of a particle in free fall, remember we have the total energy and the gravitational potential energy both plotted. Okay. Now we can still figure out what the kinetic energy is because the total energy is conserved, right? So if we know the total energy, which we do from the plot, and we know at any given height of this thing in free fall, if we know its gravitational potential energy, this is a simple subtraction, right? So actually we can calculate K by taking the total energy and subtracting out the gravitational potential energy. Okay, now this is actually pretty useful. So instead of having the total energy plotted, the kinetic energy plotted, and the potential energy plotted, we can sort of keep these graphs clean by just looking at the potential energy and the total energy while still being able to get the kinetic energy out. So let's take a look at this plot here. Over here on the right, so we do have the particle in free fall, and we're plotting its potential energy as it changes in height, and of course its total energy. You'll notice the total energy remains constant. So I'm going to write constant here for the total energy. And you'll notice that the slope here of our energy, the blue line, So this is just y equals mx, right? No b, b 0 because it goes through the origin. But look at what we have here. We have mg, okay, our horizontal variable is y. Okay, so it turns out our slope is just the weight of this object, right? So we have the mg of the mgh, that's going to dictate how steep the slope is for our potential energy plot. Okay, so here at the origin, the potential energy is 0, which makes sense. Okay, so here at the origin, where this thing is on the ground, the height, notice that the height is on the x-axis. But here at the origin, the height is 0. There is no potential energy. It's on the ground. This line goes through the origin. That totally makes sense. Okay, now what does that tell us about the kinetic energy? So this means that all the energy is kinetic. Okay, so all that energy is still in there. This object is not like at rest or anything. It just has no potential energy. So to keep the total energy, because remember our total energy is the same right here in red, that never changes. So to keep that total energy, if we have no potential energy, it all has to be kinetic energy. Okay, so at the origin, the speed of the particle is at its maximum. Okay, so at the origin, we can tell from the plot that the kinetic energy is at its maximum. Okay, now as we start moving this object up, or as it moves up, since it has this maximum velocity, maybe it's heading straight up. As this thing heads straight up, notice what happens. So over here, let's say at y1 on the plot, so we have a little bit of height now. So that means we've gained a little bit of gravitational potential energy. But remember, it's still moving, so it still has some kinetic energy. We can calculate that by taking the total energy and subtracting out u. Okay, so let's do that. We can take the total energy. Okay, now we're going to subtract out u, which is the red here, the gravitational potential energy, and look at what we're left with. We're left with the blue, and that's actually the kinetic energy. So the idea of this plot is essentially on one side of the potential energy curve. Okay, I'll do this in orange. So on one side of this potential energy curve, you have your potential energy. So everything up to the line, up to the slope is your potential energy. And then on the other side, let's do red. Then on the other side, everything's kinetic energy. Okay, so that's how you can actually get both pieces of information out of this one plot, even though you're only plotting potential energy and total energy. Anything above it is kinetic, anything below it is potential. Okay, so that means here, going back to the origin, you can see now at the origin we have maximum kinetic energy. Now, something else to think about is what happens when the particle gets to its maximum height, okay? So here, when this particle gets to its maximum height, all the total energy is gravitational. There is no more available kinetic energy. And you can see that from the plot, which is starting to get a little crowded, but you can see here when the line crosses the total energy, I'm running out of colors. There we go. So when the line crosses the kinetic energy, or when the gravitational potential crosses the total energy, the distance is 0, so that means there's no more kinetic energy. All of this is gravitational potential. Okay, now notice that this line, the blue line, does go on past the total energy, but it doesn't make physical sense anymore. Okay, it's not possible for the gravitational potential energy to be greater than the total energy, because that would require the kinetic energy to be negative, right? Because the total energy has to be the sum of the two. So if the potential energy gets too high, we have to have a negative kinetic energy to cancel it out. So you can see over here in the top right of my plot, this little area here, that would mean a negative kinetic energy, and we just can't have that. Okay, so even though the plot goes on, we have to stop interpreting the plot right here when the potential energy and the total energy cross. Okay, so since kinetic energy can't be negative, that's why we're stopping there at that intersection. Okay, and this intersection is actually a turning point. So when TE, the total energy equals UG, this is a turning point. Okay, so let's look at an example really quick. So the same thing, we have a ball, we just have pictures now. So what's going on is we have all this initial kinetic energy going up from the origin. Okay, now there's no potential energy. We can see that here. No potential energy, it's all kinetic. This is the maximum velocity of the ball because all of that total energy is purely in motion. Now, as this ball starts moving up, it's going to have a balance. It still has a velocity up, but it's also above the ground. As you can see, it's above the ground. We've got some height to it, so it's going to have a mix of potential energy and kinetic energy. So we've got that labeled here, and as you can see, we've got some potential energy. So I can label my potential energy here. And then at the same time, it also has some kinetic energy because it's still in motion. And you can actually see that here in the bar plots. It's got, looks like a 50-50 mix of potential and kinetic energy. And then this ball, since it still has a velocity up, it's gonna keep going. Okay, so by the time we get to this fourth frame, we see that it's actually reached its maximum height. And we don't know what that maximum height is since we don't have any numbers to plug in, but we can still conceptualize this. So here at its maximum height, you'll notice the velocity is 0. And anytime a velocity is 0, that means there's no kinetic energy. Okay, we can see that in the bar plot. So here's that turning point. And this makes sense why it's a turning point. This thing, this ball, when it was thrown, has lost all of that velocity because gravity's acting on it. So here it can't go any higher. There's no way this can go any higher. That's why this is where the turning point is. So here's our turning point. That's where our two plots cross, and that's why it maxes out. There's literally no more energy to go any higher. Even though the plot, we can plot it, we can plot it to the moon if we wanted to, but it only makes physical sense below the total energy line. Okay. Now we have all of this potential at the top. Same process is going to happen backwards. This ball is going to fall, gain some more velocity. So again, we have this healthy split between the potential energy and the kinetic energy. And essentially, as this ball falls in the physical world, graphically speaking, we're going to ride this potential energy slope down. So you'll notice that the positions here on this blue line, literally it rides it up, hits the turning point, and rides it back down graphically, just like the ball might be doing as we throw it up and down. Okay, so that's the idea of just the energy diagram in free fall. So let's do another example where we're looking at an energy diagram of a particle on a spring. Okay, so this is going to be a particle or a mass on a horizontal spring. Okay, so we're thinking about something like this, and maybe it's connected to a wall. Okay, so now this mass is free to move left and right. Okay, now let's consider the energy of this mass on the spring. So we know that the potential energy of the spring is going to be 1/2 k delta x squared. Okay, this is a potential energy because it's based on position. Okay, so if that's our potential energy, what might our kinetic energy be to give us the total energy? Okay, so we're after this. We want the kinetic energy of the system plus the potential energy of the system gives us TE. Well, we've got the mass on the end of the spring. We're going to assume the spring's massless. So the mass itself on the end of the spring is going to have some sort of kinetic energy. It's moving horizontally, so there's no way for it to gain potential energy. So the kinetic energy is just going to come from the mass, but the potential energy is going to come from the spring. Okay, and when we add these up, we get our total energy, which in this system, there's no friction, so the total energy is conserved. It will be the same no matter what happens. Okay, now the last plot was really easy. So let's see, last plot. The last plot was just linear, right? Because that's just mgh. Okay, well, the slope of this was just mg, and then our variable that was changing was h, or height, h, or y, however you want to say it. This example is going to be a little trickier. So what we're going to do is we're going to plot our potential energy, which is the 1/2 k delta x squared, okay? Now, we're going to plot that over here. I'll draw it in blue. So you'll notice since delta x is our variable, and it's squared, that's going to be a quadratic. It's going to have that like ax squared look. So that's why our potential energy curve is now going to be a quadratic. Okay. Now, you may remember from Algebra 2, since this term is a x minus x equilibrium, the delta x, this term here is not a variable, it's a constant. It has one equilibrium position. That's telling us where this parabola is going to be centered in the plot. So that's why it's centered right here at x sub e. Okay, now the value of k is actually going to tell us how open or closed the parabola is. So if we had a really high spring constant, we'd get a really skinny plot. If we had a lower spring constant, this parabola would get wider. Okay, so we've got where the parabola sits is determined by the equilibrium position, and how wide or skinny it is set by k, the spring constant. Okay. So remember, and this is interesting, no matter where this end of the spring is and the mass is, whether it's being stretched or compressed, because we have a v squared and a delta x squared, these energies are always going to be positive, whether it's being like pulled or pushed to the right or the left. No matter where it is around this equilibrium position, we always get positive energies, which is why we have a parabola turned up. No matter where you go, the parabola doesn't dip negative into negative energies. It's always going to be positive. Okay, now let's take a look at what's going on. So we have this position to the left, XL, and we have this position to the right, XR. And you'll notice these positions are actually where the potential energy curve and the total energy intersect. And we've already said that these are turning points. That's where the total energy equals the potential energy. It's the same value. Okay, when we have all potential energy, there's no kinetic energy. Okay, so at these turning points, XL and XR, this mass is not moving. Okay, now think about it. Just visualize a turning point. That means we have this mass, it's being pulled back on a spring, or maybe it's oscillating. Well, after it goes out so far to like the maximum stretch, for just a brief moment, its velocity is 0, and then it heads back, right? So you can imagine here, we start moving to the right, okay? But then after this mass on the spring gets stretched out, it's got to head back in the other direction. So this is our turning point. This is where we have no more kinetic energy to move it further out. Okay, so that's why we have these two turning points on either side, because the spring can go either way. And I will stress again, this is where there's no kinetic energy, it's all potential energy. Okay, so let's look at another couple of frames, this time using the example of the mass on the spring. Okay, so let's say we start over here at this one turning point on the right. Let's say maybe we've grabbed this mass and pulled it out and we've not let it go yet. Okay, so it's got potential energy. Actually, it's all potential energy, right? We've added the potential energy in because the spring has been stretched, but we haven't let it go yet, so there's no kinetic energy. Nothing's moving. We've just essentially charged it up, so to speak. So you'll notice in this situation, we have all kinetic energy. This thing is not moving. That's why this bar is 0, the kinetic energy bar. Okay. Now we're going to hold it here, let it go, and as soon as we let it go, it's going to start losing potential energy. So you'll notice in our second bar plot, we've lost potential energy, but we've now gained potential energy. We've got a plus K now, okay, because we're actually starting to move. So it looks like we have more kinetic energy than potential energy, and you can see that here in the plot. Remember, this is our potential energy on one side. This is our kinetic energy on the other, so we have more kinetic energy than potential energy as we're moving to the left. Now, right here, as we pass through the equilibrium position, well, in the equilibrium position, we have the spring, that's where the spring wants to be, okay? So the spring wants XE. The spring wants to be at equilibrium. So as soon as it gets to equilibrium, it doesn't have to do its job anymore. We have no spring potential energy, okay? But we do have this kinetic energy. So since the spring in this position at equilibrium decided to take some time off, the energy has to be made up by the ball, the moving ball. Okay, remember we have to keep that TE value. No matter what, TE has to stay the same, the total energy. So since right here equilibrium, the spring decided to take the day off, the mass at the end has to make up all that energy to get us to TE. And you can see that in the graph. This is our kinetic energy, and it spans from 0 energy all the way up to TE. Okay, and we can see that also in the bar plot. There's our kinetic energy. It's the real MVP as we pass through the origin or the equilibrium position. Okay, so now once we do that, the spring decides to do its job again because it's been displaced. So we now have another delta X. So the spring jumps back into action and says, oh crap, I can actually provide some potential energy here. So you'll see that in the fourth bar, the potential energy jumps up a little bit, and we actually start losing. So this was our total K. We actually lose a little bit of kinetic energy here. But of course, if we were to add these up, we would still get the total energy. And this is also reflected here in the plot. You can see we get just a little bit of potential energy down here. And at this particular moment, quite a bit of kinetic energy. And this process, if it's frictionless and everything, and you're not losing any energy, this process will go on forever in this oscillation. So essentially what's going to happen is you're going to ride that parabola. Graphically, your point is just going to ride the parabola back and forth from turning point to turning point. Because when you hit that turning point, that's where there's not enough kinetic energy to move the spring any further. Okay? So you're going to bounce from turning point essentially forever. Now let's do one more quick example where we're just thinking about these energy diagrams just in general. One general example, I'm not even sure what this energy diagram might be showing in the real world. I don't know, don't care. We can still understand the system without having to know exactly what the system is or physically what it's doing. Okay, so let's consider this general potential energy and total energy plot here. You can see the potential energy does some really weird stuff. It's got some moves in it here. It's got some curves. Who knows what's happening? But we can still get some information out of this. So the slope of the potential energy shows where the particle is speeding up and slowing down. Remember, we can actually rearrange our total energy equation and just say that the kinetic energy is just all the energy with the potential removed. Okay, so it turns out as this particle moves from rest, okay, so we're up here. Now, how do we know it's at rest? Because it's at a turning point, okay? When you're at a turning point, there's no kinetic energy. So it has to start from rest. Now look at what happens here. As we move from x1 to x2, we're speeding up because we're getting more and more kinetic energy. Okay, so you can see as we're moving, the distance between the total energy and the potential energy, that's getting bigger, which means we're gaining kinetic energy, but it also means we're losing kinetic energy, or sorry, we're losing potential energy. But now what happens over here? So from x2 to x3, this means we have to be slowing down because we're gaining potential energy, which means we're losing kinetic. So if one of these grows, the other one has to get smaller. So that means for us, we've lost kinetic energy. So that's a minus K right there. And then we can keep doing this over and over again. So it turns out whatever's going on between x3 and x4, this is interesting. So what happens is we keep speeding up until look what happens at x4. At x4, we lose all of our potential energy. So I'm going to grab another color. So at x4, we have no potential energy. All of that is kinetic energy. So actually at x4, that's the maximum velocity. Okay, now after this object moves past x4 and gets to x5, it's got to stop and be at rest again because it hits that turning point. It hits the other turning point. So here at x5, there's no velocity. So there's our other turning point. Okay, so this object can actually just move back and forth between these positions all it wants to because it's stuck between two turning points. Now some of these points here have have special labels. Okay, so it turns out that point 2 and 4, x2, x4, these are stable equilibria. Now let's look at them. Okay, so essentially, if you put your particle here at x2 or x4, and you sort of give it a small change in position, so a small change in these positions will actually just cause the particle to oscillate. So essentially what that means is these are actually little equilibria, just like springs. So if you were to, I'm going to try and zoom in without crashing everything, but if you were to put a particle in here, and if you just gave it a little push in either direction, this particle would oscillate just like a spring because this is a stable equilibrium. It's a dip. The particle is happy here. Essentially, you're minimizing changes and transfers of energy between kinetic and potential. So if you were to drop a particle here at x2 and only give it a little push, it would want to oscillate around x2 and it would want to hang out there. Now, if you gave it a big push, you could get it over that hill and over that potential. Right, a big push, you could send it on its way again. But if you're just giving it little pushes, it wants to stay around that stable equilibrium. Same thing down here. If a particle gets to x4 and you just give it a little tap, it's just going to oscillate back and forth. It's kind of happy in this stable equilibrium. And with a potential energy plot, these equilibria, the stable ones, they all have the same shape. They're essentially a parabola pointed up. Okay, so that's a stable equilibrium. Now you can imagine for x3, this is an unstable equilibrium, which means, and it kind of makes sense with the picture, if you were to put a point or a particle right there and you give it any sort of push whatsoever, you're going to lose it. It's going to want to take off on you, and it's going to speed up. Remember, as this particle moves in either direction, we're going to gain kinetic energy. You can see here, see where we're gaining kinetic energy because it's down from the total energy. So the whole idea here is this is an unstable equilibrium because you can tell from the plot, any push in either direction, it's just going to want to keep speeding up no matter what. Okay, so I'll circle this in green. So that's our unstable equilibrium. Okay, so position x3 is an unstable equilibrium, and essentially this is just a particle placed at this exact point will not move. Now, in the example of a stable equilibrium, it will move because it'll oscillate. But with the unstable, it's going to sit there perfectly until you add any small change, and then the particle is going to want to move away. So that's the two differences here between a stable and an unstable equilibrium. All right, just to sum everything up and how we interpret these energy diagrams, I'll go through these pretty quick and then we will call it. So the distance from the axis to the PE curve is the particle's potential energy. So, ooh, different color, different color, different color. So all that means is the distance from here to here. That's the potential energy. And then the distance from the potential energy curve to the total energy. All right, so here's my total energy. Anything here and above, that's the kinetic energy. Okay, so the sum doesn't change. And that's important. When there's no friction, everything's conserved. So a point where the total energy and the potential energy cross is a turning point. So you can see here, we've got this crossing point. So that's a turning point, okay? That means the particle must reverse direction. There's no more energy to keep it going in the direction that it was going, hence the name turning point, okay? So the particle cannot be at a point where the potential energy curve is above the line. So anytime when you have this situation, any information up there doesn't make physical sense. It has to stay below the turning point. Now remember, the PE curve is determined by the properties of the system. So in one case, we had the potential energy of an object in free fall, which was linear because of the mathematics, the mgy. And then in another situation, we had the 1/2 k delta x squared, which was a parabola. And of course, like the m in this equation or the k in the other one, that's actually going to set up what your graph looks like. So do remember that a minimum in the potential energy is a point of stable equilibrium. And then a maximum in the potential energy curve is an unstable equilibrium. All right, so no examples, no tricky math. This was all conceptual just to get you to start thinking about how you can take a physical situation and think about it in terms of bar plots and graphs. So these are actually very useful. You can actually reduce a fairly complicated problem down to, just a simple plot. And if you're good at interpreting it, you can actually learn quite a bit about the system. So as always, if you have any questions, let me know. This is the end of our introduction to energy. The rest of the time throughout the course, we're going to be using this idea, but as of right now, you officially have a good understanding of the basic concepts of energy and conservation of energy.